All right. Well, good morning or good afternoon, everyone. Thanks for joining today's webinar on integrating transportation, energy, and emissions modeling across spatial and temporal scales. My name is Mike Centetos. I'm the Policy Director for the National Center for Sustainable Transportation. I'm going to be moderating the webinar today. This is part of a monthly series that we put on, and you should certainly stay tuned for upcoming webinars. The National Center for Sustainable Transportation is part of the University Transportation Centers program, which is administered by the U.S. Department of Transportation. We're a consortium of 6 universities around the country, one of which is Georgia Tech. We focus on advancing environmentally sustainable transportation through cutting-edge research, direct policy engagement, and education of our future leaders. We've got a mailing list, so you can get notifications about our upcoming webinars and current research and other events. It's at ncst.ucdavis.edu. Today's webinar will take an hour. We have a presentation from Randy Gensler, and then we're going to open it up to Q&A from all of you. So think about your questions as we go along. We have a Q&A feature in the Zoom webinar platform to type in your questions. You should be able to see it kind of on the bottom toolbar of your screen. So feel free to type in your questions as the webinar, as the presentation proceeds. We'll save our Q&A for the end, but please get your questions in as you think of them. We will be recording this webinar, so it'll be available along with the presentation on our website shortly after the webinar is over. And with that, I'd like to thank welcome our guest and our speaker today, Randy Gensler. Randy is a professor of civil and environmental engineering at the Georgia Institute of Technology. And Randy, I will turn it over to you.
Thank you. Thank you very much for inviting us to participate today. I'm joined here by Dr. Haobing Liu, and most of the things that you'll see today, he has made work. So everything when we talk about working with the supercomputing cluster and Python scripts and the capabilities that we developed, Haobing's been responsible for a lion's share of that. Also by Daijin Kim, who's one of our senior PhD candidates. He's been working with the AirMod microscale dispersion model, and you'll see some of the gridded applications that we developed later on. So the presentation today really is going to focus on the integration of various models at different spatial scales and different temporal scales. Using what we call moves matrix, which I'll talk about in a minute, just a fancy pre-run version of moves through all the different possible inputs. And a lot of that research was sponsored by the National Center for Sustainable Transportation, or NCST, but also a lot of it came out of an ARPA-E project that we had with the Department of Energy, about a 3-year project, with a number of $1 million to develop regional simulation modeling for the entire metro area, and then to be able to link in energy and emissions modules that would work in real time with data as they flowed in. We're going to talk about moves matrix, which we use for both energy and emissions in 49 states, every state in California. I'll also mention the Georgia Tech fuel and emissions calculator, which we use for some of the upstream emissions and energy activities. Really what it is, it's the integration of both GREET and moves matrix within a spreadsheet and online calculator system. And we'll talk about the applications across travel demand models, traffic simulation models, the micro simulation like BISIM, but also some of the more macro simulation like dynamic traffic assignment, and any kind of a simulation model that moves platoons around a fleet or individual vehicles can be connected with moves matrix. Data-driven real-time simulation, monitored corridor level activity, and then finally we'll end up with some of these dispersion models. And I'll mention a couple of the dissertations that have been recently published, what we've been doing there, and you'll see publications coming out on those. So let's talk about moves briefly. A lot of you probably already are very familiar with moves. Moves is basically a modal emissions model in that you're actually calculating the vehicle-specific power for the vehicles that are operating on a roadway as a function of each vehicle class and the characteristics of operation, which include speed and acceleration. But also it involves road grade. And most applications assume that the world is flat. So you'll see some slides later on about how we are moving into the realm of integrating grade directly. And it does make a difference. It makes a difference both in terms of how some of those vehicles operate. In other words, the acceleration characteristics of some of these vehicles are different going uphill than downhill, as you might suspect. and that translates into differences in vehicle-specific power and therefore energy use and emissions. So the bottom line here is that because moves is translating your inputs into this VSP framework, and then operating within the model and then translating these things back out into emission rates, we wanted to develop a system that would allow us to do things a little bit easier than working with moves directly in each application. Moves models emissions and energy use across 13 different source types. And so when you run moves, you're going to get different emission rates for each of those vehicle classes, and you'll get different emission rates for how those vehicles are being operated. If you look at the just a typical emissions rate in grams per second, you can see that we've got 23 different operating bins across there. They're numbered from 0 to 40, but there's some that are missing. And really, it's divided into a couple of different regimes. You've got 3 different speed regimes, a low, medium, and a high speed regime. And then you have the VSP calculation using the equation up at the top. And as you move up in VSP, you move along those bins from left to right. You've got a braking bin, you've got an idle bin, and you've got low speed coast and medium speed coast. And then as the VSP increases, you can see that each of those curves upward to higher gram per second emission rates. So the bottom line with moves is that if you can specify the way that first you specify what the vehicle fleet looks like and break those down into the individual vehicle classes. And then you specify the model years for those vehicle classes. And then you specify the way that those vehicles are being operated, whether you have an average speed and a driving cycle that goes along with that, or you have individual second by second data, you can actually calculate the VSP for those roadway operations. This animation here is the federal test procedure, the driving cycle. And what we have going on in the upper bound there is the speed, second by second speed over time as the vehicle is driving along on the laboratory treadmill. And you can see that for every second of operation, the VSP is being calculated, and you have the bins of VSP operation down in the bottom. So those correspond to the 23 different bins numbered from 0 to 40. And if you look on the very bottom line, you can see the instantaneous speed and acceleration, the current energy consumption, total distance traveled, and the trip energy accumulated over that time. So we've basically been able to hook in with moves and those moves emission rates to be able to operate the characteristics, the underlying characteristics of moves at different spatial and temporal scale. So if you've used moves, whether you've used the old mobile model or any of the new moves models, modeling complicated networks is really kind of a challenge. And it becomes kind of tedious. It requires that you generate different emission rates for different vehicle operating characteristics. And traditionally, modelers have either tried to simplify things by, I don't want to say dumbing it down, but by aggregation to say, well, we're going to assume that all vehicles are driving under the difference between these 2 driving cycles embedded in the use and average speed of facility type. We're not going to care about whether or not there's a difference between the different vehicle classes in terms of their operations on the road. And maybe we'll use one distribution of model years for all of the vehicles, or at least for all of one source type. So we either simplify the inputs, or we create these lookup tables to support the modeling that we do want to do. And that generally consists of running moves for those scenarios. Let's say, I want to have an emissions rate for 25-mile-an-hour average speeds on arterials that I can apply in Cobb County, because the fleet is different in Cobb County than elsewhere. You pre-run all of those different conditions that you want, generate your lookup table, and then apply the lookup emission rates in the modeling that you're doing. So the goal here with moves matrix really was to pre-run moves for all of the different combinations of input data. So configure it for distributed computing so that we can take advantage of multiple cores on a supercomputing cluster. Iterate the inputs across all of those different input combinations and run moves thousands of times for a region in advance of having to do the modeling. And then compile all those outputs, those energy use and emission rates, into the multidimensional matrix, so that's moves matrix. And then finally develop a series of scripts to then apply these matrices to any analyses that we want to run. For a metropolitan area, it takes about 30,000 moves runs to do the on-road exhaust emission rates and energy use. So this is not the hot soak, it's not the extended idle, it's none of the other supplementals. We'll talk a little bit more about that later on, but it takes an awful lot of moves runs to do this. It's across 21 calendar years. In Atlanta, we have a summer, a winter fuel, and a transition fuel for a number of months as we go from the summer to winter and back. We're doing 23 temperature bins, so 5-degree Fahrenheit increments, and 21 humidity bins. It takes about 20 minutes per core per run, so about 5 days to process all of the different emission rates or all the different input files for Metro Atlanta. And that's given, we get about 80 cores at a time that were assigned by the computing cluster that I'll show you in a minute. The bottom line is we're generating not hundreds and thousands and millions, but 5 billion running emissions rates per region. So it's a pretty good sized matrix. It's 121 gigabytes. We've done more than 1 million moves modeling runs, probably about 1.1, 1.2 million modeling runs to date to generate the state of Georgia, state of Texas, Vermont, a variety of different locations across the United States. I should point out that this is assuming a fuel specification program and assuming an inspection and maintenance program. So for each modeling region, if they have a different fuel specification or inspection and maintenance program, you have to do the 30,000 moves modeling runs. It turns out that across the United States, there's 117 different combinations of fuel specification and inspection and maintenance program. So running moves matrix for the entire country is a little bit daunting on an 80-core supercomputing cluster assignment. So much larger computing clusters are needed to generate everything for the entire nation. But we've been responding on demand as folks need applications. We will develop the models for their region and send them the results on an external hard drive, 121 gigabyte matrix, and all the Python scripts that they need the process. So the way that we do this is through what's called the PACE supercomputing cluster. It's actually a co-op more than anything. Faculty members that want to participate in the co-op, they have a research project that will provide funding to purchase cores, new cores for the system. I'm not sure if this is a sustainable system because as old cores go out, new cores have to come in. I'm not sure if this is a pyramid scheme or not, but the bottom line is you buy your way into this, and then you're assigned cores based on the number of cores that you've donated or contributed, and then excess time on cores are made available to individuals as a function of being online and availability. It's a pretty good size system. We have a new system that's just been implemented over in a new building that's been constructed on campus. We're looking into how to get onto that system that's much larger and much faster, but this is still an outstanding resource for us. I would also say that one of the big benefits of this supercomputing cluster, and I can't recommend it highly enough, is the fact that they have staff that are stationed at PACE that work with the researchers. So these are not just computing staff, these are research staff that operate out of that system, and we collaborate with them on a variety of different projects. So they're great to work with and provide a lot of really good support. And they also tell us when we're breaking the system, which is another, it's an advantage for the overall system, not necessarily for us. We have found that that MOVES is not structured as efficiently as it could be for operating on a supercomputing cluster. It tends to consume more cores than they would like to have us consume. And even though operating on multiple cores makes our individual runs go faster, and, it's taking up a number of cores that are then not available for other folks to use is not in the best interest of the collaboration or the cooperative. So we've been working with them to get down to a single core process, or at least a 2-core process, so that we can reduce the essentially the demand that we're putting on that system to do the runs. Each run will take longer, but overall, the overall system will become more efficient by doing this. They've been great to work with. So if you look at what comes out of that modeling process, you do those 30,000 runs and you generate this 5 billion cell array of emission rates. Those emission rates are stored by calendar year. Fuel and IM program is a whole set. And then the meteorology in that. And before you do an operating run, say you're trying to connect this matrix of emission rates with a travel demand model or a simulation model, you predefine what the calendar year is that you're going to look at, or multiple years, your fuel and inspection and maintenance program, the temperature, the humidity, and you pull essentially a subset of that big, huge matrix to work with. And the Python scripts that the folks here have developed do all of that. Once you have that, and you have that subset, it becomes a lot faster to work with. And if you look on the bottom line of this chart, the blue is the query that we're doing of those submatrices. So if you have the source type distribution, so you have the vehicle classes, and then for each of those vehicle classes, you have their model year distribution. And for each of those classes and model years, you have the way that the vehicles are being operated, either the operating mode bin distribution by VSP or an average speed and emissions rate, for which we reassemble the moves component. You can go in and get the emission rates that you need. So think of it this way. What we've done is we've really pre-run moves for all the different combinations that we would potentially be using. And then we've developed script to go into that array and pull out the emission rates that we need on a link by link basis. And the advantage of this is that we get exactly the same results as using moves. We're really, all we're doing is outputting all of the possible combinations, and then we're reassembling those combinations in the exact same way that moves does before it gives you your gram per second or gram per mile emissions rate. And I don't know about you, but I don't think I've ever worked with a project where the R squared was 1. It is a perfect match, which is great. So the difference is that you see at the bottom, they're only associated with rounding, and that's not 0.01%, that 0.0001%. So it's an excellent match. We also developed for the Atlanta metro area, not for any other regions, what is known as Moves Matrix 2.0. We knew that we didn't have the start exhaust emission rates in there, truck hoteling and evaporative emissions, and we wanted them to be able to do regional emissions inventory analysis for Atlanta, for the metro area. So yeah, we have the running exhaust that we can do for anywhere, but doing this for all of the start and soak and all of those emissions takes a lot longer. As I recall, it takes about 20 days on the supercomputing cluster to generate the matrices for a region, and the matrices are huge. They're absolutely huge. But we have done it. We're capable of doing it for any region. It's just a matter of having enough supercomputing time in order to generate the rates for other folks. And again, get the R squared of 1. It gives you a lot of flexibility for use in scenario analysis, though, when you do you have this inventory to work with. So, you know, for example, if I want to know what the on-road emissions are, you know, that's a lot easier. But if I want to look at a new plan, a transportation plan for the metro area with a build out for 2040, and they're talking about making major modifications in the structure of the transportation system, we can do the on-road fairly easily, but now we can also bring in the exhaust and the evaporative emissions and do the full inventory, which is what the regional planners do need. So before we move to some of the applications, I do want to mention that we've also developed what we call the fuel and emissions calculator. This is an NCST sponsored project. It originally started with a funded project we did for the Federal Transit Administration. And so it's a combination of moves matrix to generate the on-road emissions rate, that's the on-road pump to wheel, but also integrates GREET, originally only for those transit vehicles, so that you could do all the upstream well to pump energy use and emissions. So you could look at, you know, what happens if you shift part of your fleet to CNG, the on-road changes, but also the upstream energy use and emissions change. So by integrating moves matrix, where you do get the ability to put in a driving cycle and have the VSP be calculated for your fleet, and then also integrate the upstream, gives you some advantages in various analyses you might want to do with respect to alternative fuels. Like I said, it was originally for transit vehicles. It does include capital costs, operating and maintenance costs, energy use and emissions. Does include hybrids and electric vehicles. So some of the things that are missing with moves, you can generate all the upstream here, and we put in estimators into the fuel and emissions calculator for those vehicles. And this should be ready this next semester to be updated based on some of the dissertation research that I'll talk about at the very end of the presentation. But it's easy to use. It's available online. You can download it, play around with it, send us any comments that you have. And the nice thing about this calculator is that you can see every single equation that's being used. It's all open source. So there's nothing going on, behind the firewall or in a black box. You can see everything that the model is doing, and you can make changes to it yourself if you want to use a different driving cycle or you want to use different assumptions about upstream energy use. Then you're capable of doing that. So with that, let's turn to some of the applications that we've developed. So you've got this on-road emissions matrix, and you've got the the full regional emissions inventory matrix available. And we've applied these at every spatial and temporal scale that we can think of with the models we're operating here in the metro area. I'll talk about the regional travel demand model, Atlanta Regional Commission's activity-based model, which is actually one of the, probably the top 5 models in terms of complexity in the United States. We've linked with that. We do a lot of corridor scenario analysis. We've done some of that for the State Road and Tollway Authority associated with the conversion of a carpool lane to a managed toll lane with an increase in vehicle occupancy. We connect directly with VISM and some other microscopic simulation models. Our preference is VISM primarily because it's got really good visualization tools, but it's capable of being connected with any simulation model that you want. We've done dynamic alignment outputs as well. And then we'll talk about microscale pollutant dispersion modeling connections. We've done CalLine 3, we've done AirMod, is what we're focused on right now. And by the time Daijin is done, we'll have connected with all 5 of the dispersion models, including R-Line. And then we even developed a little app component for the ARPA-E project, which allowed us to look at energy and emissions use in real time and pre-planning of travel across different routes and time of departure and modes, so including even park and ride to transit, so that you could look at what the energy use and emissions differences are across those. So I would mention also that the fuel emissions calculator and the cost calculator can be, we have 2 different models there that I didn't mention the cost calculator because I had to pick the slide out for time, but we have a really good online cost calculator that is available through NCST as well. So you can see how much it costs to own and operate your vehicle over the life of the vehicle and cent per mile. Anyway, these other 2 models can be applied in series with Moves Matrix. So it gives you a lot of powerful capabilities in terms of looking at changes in energy use, operating cost, and the like. Okay, so Moves Matrix 2.0 is what connects to the travel demand model. We model the 20+ county metro area. Some of these counties got a couple new counties that are coming in. The main planning area, the biggest population densities are in the white area there, and the newer counties that have been added over time as the metro area has expanded are the counties in brown over to the right. The model is pretty complicated. It's mostly choice-based for all of the algorithms. So even the number of trips generated per household is a choice. The probability that you'll make 1 trip, 2 trips, etc. The trip distribution model is also choice-based, so it's the probability you'll go to a zone over to the northeast versus a zone to the southwest, so not just a straight gravity model. Traffic assignment is pretty much the same as we've had in the past, using Frank Wolf algorithms to distribute those trips through the network. But then mode choice is a choice-based model, so it's quite complicated. The model that is currently in circulation has 5,800 zones, transportation analysis zones, and about 74,000 network links in the link and node structure. The new model that was coming out, the one that we've been working with for most of our applications, has 202,000 links. Fortunately, we learned the same thing that ARC has learned, and that is that 200,000 links is too many links. The latest model that will be coming out will have about 138,000 links in the next generation. But also the number of analysis zones are increasing. So for any of you who run a travel demand model, you can recognize these are very large numbers. This is a model that runs overnight, more than 24 hours to do the modeling runs. So scenario analysis is a little bit cumbersome. But the nice thing is that by being able to connect directly to Moves Matrix, again, Moves Matrix 2.0, you can then take the outputs of that model and automatically generate the emissions inventories. And you can do it by pollutant type, and you can do it also by source type within the pollutant type. So here you've got the output for the on-network and off-network emissions for, you've got the VMT, hydrocarbons, and PM. And you can see that you've got the start emissions in the lower left, and then the parked vehicle evaporative emissions, parked vehicles and the evaporative emissions for hydrocarbons, PM 2.5 for the off-network. So it allows you to then look at where these emissions are occurring. So you got your spatial component and your temporal component, because the travel demand model is actually saving every single trip, 20+ million trips in the metro area across the day. And then by running that model and applying the lookups in Moves Matrix, you can break this down by hydrocarbon source types, so start exhaust, evaporative permeation of the gas lines, fuel leaks, etc. And on the PM side over there, you've got brake wear, tire wear, running exhaust. All of these can be automatically generated by linking these two models together. Our ultimate goal really is to be able to take any scenario analysis that comes out and automatically run it with moves matrix in background, so that the next morning when the modelers come back in, they have not only the outputs from the travel demand model, but we've automatically generated all of the energy use and emissions that go along with that network. So microscopic simulation modeling is the next. VISM is one of those more complicated models. It involves car following algorithms. So each vehicle is moving through the system. VISM actually tracks the location and the position and the time of that vehicle's movements. And it's integrating things like weaving and distance separation, braking, and all of that. And so if you integrate through the COM interface, which Mike Hunter and his crew upstairs do a lot of that, you can basically retrieve the vehicle trace data out of the network file. So you can see for every single vehicle what the speed and acceleration characteristics are of that vehicle as it's moving through the system. And so that it gives you a lot of capabilities with clearly directly calculating the VSP and STP for the heavy duty vehicles, and then applying the energy and emission rates from moves matrix directly. Now, there is, VISM doesn't assign directly the same source types that moves uses. You get heavy duty vehicles based on your inputs, and you get the light duty vehicles. And so there is an overlay that we do in order to match up the fleet characteristics with what we're getting out of the COM interface. We do have a little interface that we use in there to basically break it down by model years and vehicle classes for moves modeling. But it's a pretty straightforward process that can be modified. So we process each of those second-by-second traces to VSP. We match the individual vehicles with the energy and emission rates that go with it. And then again, through the COM interface, we append the data back to the trace data. So you get, in the output file, you then have the ability to look at the animation of energy consumption or emissions. This is for CO2 emissions, so energy consumption as well. You can see that we've got the individual vehicles being assigned to the network. You've got the motorcycle as the diamonds, light duty vehicles over there as the circles. And you can see the combination trucks of the boxes. And then over on the right, we've got the coding that goes with the color coding that goes with the emission rates in grams per second. If you look closely at this, you can see that you have emissions increasing during the acceleration phase. You have emissions increasing at high speeds. But really what we're doing is calculating the second-by-second VSP for all of those vehicles, applying the emissions rate, and then animating that output. So you can use it both for comparative analysis for scenarios, like you're going to change the highway operations design, you're going to add a lane, subtract a lane, change a weaving section, all of those things that VISM will allow you to look at, and then you can generate the energy and emissions changes that go along with that. AirMod is the pollutant dispersion model that we're currently using. This is what Daijin has been working with on the supercomputing cluster. We use it both for air quality impact assessment for things like environmental impact assessment, comparing across alternatives, for conformity analysis, and for health impact assessment. So the goal here really, because AirMod is another one of those models, it takes a while to run, is to try to speed up the operating characteristics of the predictions of downwind pollutant dispersion from vehicle activity, and then to also do some link screening, which we'll come back around to, basically ignore those links that aren't contributing emissions at a receptor that you're interested in. So AirMod for microscale dispersion is available free for anybody to use, and we'll talk a bit about how we do the worst case pollutant concentrations and identify hotspots. So what's going on here is a linkage between the traffic volumes observed on Jimmy Carter Boulevard and the hourly CO concentrations that result. This is for a weekday in 2012, where the background concentrations are excluded. And the concentrations are not high, they're not super high. They get up quite a bit up at the peak of the peak. And in terms of the regional scale applications that we've been doing, and we'll talk about how we speed up those processes in a minute, if you look at the time it takes to essentially look at the impact of every single link on every single receptor, where you've got a grid of receptors over the metro area, it takes about 10 days to process on the supercomputing cluster. So think about it. We've got an awful lot of links that we're talking about that break down to 161,000 individual polygons for air mod analysis. We've got 1 million receptors that we overlaid on this grid. So it's quite a computational process. You can do a worst case analysis using the highest emissions rate selected, and it only takes about 3 days to process that. But you have the capability of both doing a regional analysis over a long period or doing a short-term analysis to get those highest pollutant concentrations. Before we move on to the next step, I do want to mention that one of the things that we've been doing is working with grade. And part of helping Lou's dissertation work a couple of years back was to develop a process and procedure for generating road grade at very high resolution over the transportation network in Georgia. We've got, for Atlanta alone, we have about 1,400 miles of freeways, 7,500 miles of major arterials, and 12,000 miles of local roads. And using the U.S. Geological Survey's digital elevation model, and a variety of techniques for smoothing, both for filtering and smoothing, and inserting roadways where you have bridges over culverts and things like that. That process allows us to get about 0.5% grade accuracy on the arterials and down to around 0.25% on the freeways. So this is really good quality grade data at very high resolution on those freeways. And the arterials. So having the availability of this high resolution digital elevation model, you can take any second by second data from observations in the Atlanta metro area, and you can assign for every second of operation, not just the speed and acceleration that you may have monitored or simulated, but now you can assign the grade to that based on the actual roadway grade for that location. I mentioned at the very beginning that it dowhat the speed and acceleration characteristics, what the grade is. So in other words, when you're, excuse me, when you're looking at heavy duty trucks, for example, the upgrade is different than the downgrade. Not as much for the light duty vehicles; they operate pretty similarly. Knowing what the grade is in terms of the VSP calculations does matter across the board here. Knowing the difference between the speed and accelerations across the grade distribution, say uphill versus downhill, not nearly as important for the light duty vehicles, but does become important for the heavy duty vehicles. So this is one of the applications that we've developed with the activity data that was collected on a second by second basis for the metro area as part of the Atlanta Regional Commission's travel diary surveys that they did in 2011. So we actually had about 500 vehicles that were monitored second by second. And then we collected data from a variety of MARTA bus lines and different activity characteristics on different routes. So it does make a difference. And you'll see that if you look at the energy consumption rate, looking at the true emissions, which is in the blue there, versus assuming that grade is at 0%, and then assuming that the activity is independent of the uphill versus the downhill, you can see that it does make a difference. We're talking about significant percentage differences. And so we recommend the use of grade. First off, we recommend the use of grade everywhere in our analyses, both for energy modeling, emissions modeling, and certainly for the microscale dispersion modeling. You can see on the right that we've got some differences in the emissions as a function of the concentrations that result as a function of uphill and downhill grade. And then like I said, we certainly recommend it for air mod for those areas where you have some significant grades. It does make a difference. And you can see the differences. Here's two different, same location, but two different runs. On the upper left, you've got without road grades, everything's flat. On the bottom left, you've got the with road grades, you have the percentage of road grade. Then you have your predictions in terms of PM 2.5 concentrations coming out of air mod. That center upper one is for flat grade, and the lower is when you include the grade. So there's some significant differences as a result. around 3 micrograms per cubic meter or so is typically what we've seen. The last thing I want to mention with respect to gridded modeling, because again, when you think about it, if you can do all of your air mod analyses for a transportation plan at once, right? If you can look at every single location in the metro area by running everything in background on a supercomputing cluster, so that when the Atlanta Regional Commission finishes running their scenario, they get the emissions inventory for the region broken down by all those different characteristics. And then they can also get the predicted pollutant concentrations across the entire region. It makes our planning processes much more agile. So here we have a comparison of what you get when you have a standard 200 by 200 meter grid, which is up in the upper left up there. And most of the applications that have been done with gridded emissions modeling and concentration modeling use these kind of sparse grids. You get the pollutant concentrations that you note there in the center up top. If you go in and you define a very, very refined gridded network, where that gridded network is kind of intelligently laid out. It's laid out with respect to having more receptors closer to the roadway, diminishing the need for those receptors as you move away from the roadway because the concentration profile drops so significantly. You end up with the concentrations in the center bottom box, and that's a big difference. So running things at a very refined scale is what we also recommend. But the problem with doing that is that you take an awful long time to run on the supercomputing cluster when you're looking at every single scepter that we've got in the lower left and every single link that's involved in there. So one of the things that Daijin has been working with is called supervised link screening. This is a tool that is essentially trying to do one thing, and that is to eliminate link receptor pairs where there's just not a significant impact from that link on that receptor. Now, a long time ago, we did it for CalLine 3 and for the old MOVES model by doing a mass flux comparison, and it was a distance mass flux combination, and we did okay with that. But with machine learning that the folks have access to now, you can really develop some refined screening tools. The bottom line here for what Daijin has done so far is that through that screening, we can reduce the air mod pace supercomputing run times by almost 99% on average. So it's a big difference in terms of being able to run those models quickly. And you're still getting 95 to 97% of the concentration being explained by that slimmed down model compared to the all link model. So with appropriate interpretation of those outputs, we think this is the way to go for doing essentially microscopic or microscale modeling over the entire metro area. And here's your fits for both downtown Atlanta and northwest Atlanta. And these are fits that, given the accuracy and that of the models, I can live with these. These are really good results. So before we wrap up here, I'd like to talk a little bit more about some of the ongoing modeling work we have going. We got 2 new dissertations that are out. One is on the use of autonomy to essentially generate VSP compatible emission rates for hybrid and electric vehicles, so that we can incorporate the modal-based activity for plug-in hybrids, hybrid electric vehicles by different type of hybrid, and battery electric vehicles into the MOVES framework. And then the second one is it uses the same kind of approach for the transit vehicles, but also includes some optimization models. Forthcoming, we have some distributive justice assessment tools coming for planning, where we look at pollutant concentrations, impact on folks in the metro area, and looking at the outputs of the model with respect to whose activity is occurring and who's being exposed by income, household size, and all the other demographic characteristics. But because MOVES doesn't currently include battery electric vehicles and the like, we wanted to have some kind of a model that would be comparable to all of that. And so Jérôme did her modeling on this. And essentially what we're doing is predicting the modal energy use for those on-road operating conditions. I wanted it to be reasonably accurate, which it is, and fairly parsimonious. We don't want to have a ton of different variables included in here. So the conceptual framework is to try to figure out, all right, we've got an energy source and energy conversion. We've got a combustion engine or electric motor, or a combination of those two. And using the autonomy model, which is a full vehicle simulation model, what Jadan did was to essentially develop a Bayesian series of models to predict what the operating mode of that vehicle is, whether the engine is on or off, whether the electric motor is being, batteries are being recharged, or if the batteries are draining. Just basically create a modeling tool to predict the operating mode. And then for those operating modes, using autonomy outputs for 50,000 second-by-second trips to develop essentially a VSP binning, a machine learning process to develop VSP binned emissions rates and energy use across both fuel consumption for hybrids as well as electricity consumption. And I have to refer you to the full dissertation to get the entire body of work. It's 150 pages or so. But the bottom line is that it does a really decent job for the fuel consumption. We can do better on the electricity consumption, but really that comes down to the specification of the vehicles that we've used in the autonomy modeling. So yeah, I know we are predicting predictions, right? We're taking a simulation model and we're taking those outputs and then we're predicting as efficiently as we can those simulation model outputs so that we can use them in the MOVE's VSP binning approach. But we think it's much better than what we have right now, which is pretty much nothing. So this is really good, and it's going to be, you're going to see, excuse me, some enhancements of this coming down the road. In looking at the application, kind of scalability components of this, she applied this again to the metro area. She used the travel demand model outputs in terms of the trips and the origin destinations, and then used an interface with one of the Google tools to essentially assign routes, and then looked at the actual energy consumption being predicted. And the bottom line is we're going to get a pretty decent reduction in energy use with the electrification of the fleet. And it was about I'm trying to remember the percentage numbers now. I think we put it on here. Yeah, we didn't. It was about a reduction of, if we can get to half of the fleet being battery electric or any electric vehicle using the assumed mix into the future, we get about a 30% reduction in energy use. So anyway, stay tuned for that. Her dissertation will be online very soon. The last tool is what we call roadway sim and transit sim. This is developed for the ARPA-E project. We essentially took the 200,000 link roadway network, coded it appropriately in Python modeling to do Dijkstra's shortest path algorithms, integrated the 90+ MARTA bus and rail routes and the 23 Greta Express bus routes using GTFS data for routes and departure times and for station locations. And with this process, basically we developed a system where you can pick any origin, pick any destination, and the system will give you the shortest path from origin to destination by any mode you choose. So you could drive direct, you could carpool to, or you could take your vehicle to a transit station, do park and ride and get on transit. But it allows you to do the shortest path modeling through the network. And so that modeling capability was translated into this new framework developed by Ann Lee for optimizing energy consumption with alternative fueled transit fleets. And so the model is now capable of predicting transit vehicle energy use, again, using the MOVE's matrix components and upstream Greek components. The simplified version of the alternative fuel or the electric vehicle simulations is really good. R² is close to 1, and the mean absolute percentage error is less than 3%. And it allows you then to assess transit vehicle performance for an array of fuels that you're choosing, like I'm going to buy a hybrid bus or an electric bus, and the routes that they're being assigned to. One of the problems that we have in Atlanta is that we have a lot of grade, and some of our transit routes are quite long, and battery electric vehicles are simply not compatible with all routes here. But this modeling tool allows you to look at the assignment of the buses to the routes, the impact of station placement, a recharging station placement, the impact of changing routes to make them more efficient, assigning buses to specific depots. It's really a fantastic model. It's got a lot of technical detail and a lot of different options to work with. So again, in the upper box, we're talking about the use of autonomy simulation to generate the microtrip energy consumption rates, and then using the machine learning to come up with that final model for applications. But the bottom line is it's a much more efficient application process and allows you to do a variety of scenarios. And so the scenarios that we have, the simplest term is just basically looking at what happens if I purchase an electric bus or a hybrid bus and assign it to different routes, and it'll tell you which is the best route that on in terms of reduced energy use. You can then optimize bus route and depot assignment. So think of it as I'm going to purchase 40 vehicles and I want to know where should those buses be assigned based on the most efficient place in the charging stations, which it will automatically figure out for you as well. And then what route should those vehicles be assigned to? And the last one, which I was really pleased that she was able to do because it was so hard, was to optimize the annual fleet purchase and assignment. So now, if you have a budget that you have, let's say you have $1.2 million for the, let's make it $10.2 million for procurement of new vehicles, it will tell you what vehicles to purchase and where to put those charging stations. And if you have extra leftover money, it may tell you to go ahead and buy that charging station that you're going to use next year. So it's another one that I really encourage folks to read. So I guess in summary, Moves Matrix is, it's not rocket science, it's brute force moves modeling. We are just pre-running that model 38,000 times and creating 5 billion emission rates to look up. So you get the exact same energy use and emission rates. It is a pre-run process that allows you then to work much more efficiently with the output. The processing time to generate an emissions rate is 200 times faster, and you don't have to do any of the coding ahead of time to figure out what your inputs are going to be for the moves model. You just have to have the inputs for pulling the results. So it's a lot easier, a lot faster. It can be applied to any spatial and temporal scale. We can quibble about whether you should apply it to individual vehicles because it wasn't really designed for that, but that's fine. If you want to look at comparisons of what the vehicles are doing on a corridor as a function of changes, we think that it's still appropriate. You can do regional analysis, corridor case studies, simulation modeling, integrate to apps. It's really quite flexible. The scripts will then link all of these traditional models with the simulation models. We've got instructions for how to operate those scripts and how to develop your own. And finally, we are linking this with dispersion models, especially AirMod Grid right now. Python scripting and coding is required. We couldn't be doing this if we didn't have folks in the lab that can program in Python. In terms of operating with the models, expertise in distributed computing, GIS visualization tools and all that helps. But we've worked with a number of customers. We've got a consulting firm that's been using the model. We're working now with Texas A&M. I know that Vermont has used the model, Iowa State. So we're here to help with respect to the implementation. And all we ask is that you send us a hard drive for us to develop the system for you. And I guess the last thing is that we've got these new energy optimization models and that we're developing based on the systems that we've created. Lots of new deep learning applications. One of our PhD students, Hangyu Liu, is not with us right here today because he's sitting over in his final exam review for machine learning. So there's a lot of machine learning that's going on in the lab. So with that, I think I'd like to conclude, and we can take any questions that folks have.
Great. Thanks a lot for that presentation, Randy. Lots to unpack. So once again, folks, if you have a question to ask, we ask that you use that Q&A feature that you should find on the bottom of your screen on that toolbar, and just type it in there. So we've got a few questions coming in, Randy. Maybe first of all, we'll start with the simplest. Could you just clarify in terms of the outputs of Move Matrix, which the types of emissions that it outputs? Is it greenhouse gases? Is it, I think you had a slide about particulate matter, NOx. What all do you get out of it?
All of them. Everything that Moves produces, we take as an output. That's why the matrices are so large. You're getting all kinds of stuff that most people will never use. But yeah, you get all of the different pollutants that Moves is capable of outputting.
Great, thanks. We got a couple of questions about how Moves Matrix factors in congestion and whether it can account for geographic or temporal variations in levels of congestion.
Okay, so think of Moves Matrix as just the outputs from Moves, right? So with respect to congestion, your congestion shows up either as a change in average speed for a roadway facility type. And let's say that I was looking at two different scenarios, one where it's congested right now, but I'm going to do some kind of a modification to relieve congestion. I may go from an average speed of 36 miles an hour on the freeway, according to the Travelman model or your simulation model, to an increase to say 45 miles per hour on the freeway. Well, moves itself, if you specify the average speed and facility type, what moves is actually doing is it's picking 2 driving cycles from its library that bound that. So let's say 36 miles an hour is the current condition. It may be looking at an internal speed and acceleration profile, a driving cycle for 30 miles an hour and another one for 42 miles an hour. And then it's weighting those 2 together. And moves is actually generating the VSP bin distribution for those 2, combining them and weighting them, and then you get the emissions rate coming out for your 45 mile an hour, or I'm sorry, your 36 mile an hour. So using average speed and facility type, you get the same results that moves would predict for congestion. If you have observational data, let's say you have speed and acceleration profiles from monitored vehicles or radar guns or what have you, you could actually generate those VSP bins yourself for the vehicle classes, and you could do that analysis. But either way, it's using the input that you give it, right? It's taking the results and saying, okay, I need the emission rates for these conditions, and then the scripts then go and get what you need from Moves Matrix. So Moves Matrix doesn't do anything itself. It's the interactive scripts between your model and Moves Matrix that give you those outputs. But yes, it does incorporate congestion that way.
That makes sense, thanks. So we also got a question about, let's see, so say a city or an urban area was contemplating a scenario with vastly fewer light-duty vehicles, transitioning to other types of transportation. The question is whether Moves Matrix would be an avenue to kind of compare the energy and emissions profile of a scenario like that, where maybe, you know, fewer light-duty vehicles, you know, passenger vehicles and more, because I think I saw on an early slide, you also have the profiles for like transit buses and intercity buses. So if you were comparing scenarios where you were kind of on a scale of an urban area, you were changing or adjusting the use of those types of modes, would Move Matrix allow you to kind of compare the emissions profiles of those 2 scenarios?
Yeah, it would, but let me add a few cautions here. So you could look at it from the perspective of the travel demand model, and the travel demand model is not terribly accurate at predicting what's going to happen on an individual roadway link. There's a lot of folks who basically say, well, we're going to run the travel demand model, and then we're also going to run dynamic traffic assignment while we're running that model, either with the outputs or as an integrated process, in order to get a better estimate of how those vehicles are going to distribute on the network and what the speed and acceleration characteristics of those vehicles are going to be. So yes, you can do it with the travel demand model, but you know, your outputs for being able to assess what's going to happen at that kind of microscale level is not great. You're really better moving to dynamic traffic assignment if you have faith that that is a good solid model. You must calibrate it for your region. You can't just take something off the shelf and run it, because it involves signal timing and all kinds of other assumptions that go in there. They're really hard to keep calibrated. Or better yet, if you're looking at a smaller area, you can go to something like this and you can look at the traffic simulation that will result. I'll give you an example. We have 10th Street in Atlanta, where we've taken one of the roadway links away and created a protected bike lane. And there's been a change. I mean, you have people that are using the protected bike lane, but you also have a change in the operating characteristics of the vehicles now on that roadway. Some of them have diverted to other routes, which may have different driving characteristics. And those that have stayed on that route have a lower travel time and more stop and go activity. So you can look at those trade-offs with respect to the system, but it's really developing the good estimate of what those traffic changes are that's key to all of this. You can have a change in traffic volumes, you can have a change in on-road operations, you can have a shift of travel to transit, in which case things will generally be more energy efficient as long as you have good ridership on those transit vehicles. But all of those things really center around the analytical work that you do on the changes in vehicle activity. Moves, again, is the tool for linking those 2 things together. So you have to have good activity change results to go with that. Now, Moves does not include bicycles. It doesn't include electric scooters, any of these other vehicles. But we've done off-model tools for the RPE project. They're really straightforward for looking at energy consumption of those types of vehicles. It's not terribly difficult to do that if you really want to. But again, it's your change in activity scenario analysis is the most important feature. Moves matrix is just your tool to get the appropriate emission rates to go with those.
Great. Okay, so the next question, I'm just going to read verbatim because it might be a little out of my depth. How do you estimate the distribution of vehicle powertrains, ages, engine displacement, and other VSP characteristics?
Yeah, so the first element is really the source type, so source type distribution. Now, what we have done, and you have a variety of different approaches you can do for this. You can look at what the travel demand model and air quality planning agencies are currently using for the fleet. And that's exactly what we did when we did the scenario analysis for the region. We wanted to use the same fleet that they use. That said, the fleet is not, I mean, you can't really apply an average fleet across the region and get reasonable results. I give you an example. When we commute from the suburbs, I live in the Midtown, but if you commute from the suburbs to downtown, you don't take your average vehicle, you take your new vehicle, your newest, most reliable vehicle, most comfortable, and it tends to be a higher model year. That tends to be a newer car. On the other hand, if you're looking at traffic on arterials and on weekends, you tend to see a lot more of the older model years. So we're big fans of doing license plate data collection and working with the agencies that have access to those data to get the make, model, and model year distributions for the fleets that are on the roadway. If you have those, they match directly with what you can do in moves. So the source type and model years can come from those license plate studies. Otherwise, you're generally using the registration mix weighted by the annual mileage accumulation rate, which is what everybody does with moves now. With respect to on-road operations, if you're working at the higher level where you're just saying, I want the average speed and facility type, we've talked about that, you just specify that and you get the VSP weighted output for those operations. If you know how those vehicles are operating, let's say you're out there with laser guns collecting data on freeways, or you're doing car following, or you're doing instrumentation of those vehicles, you can take those speed and acceleration characteristics and use them as well. So think of moves matrix as really you're specifying what does my fleet look like in terms of the source types, the cars versus trucks versus different kinds of heavy duty trucks. Then what's the model year distribution within each of those, depending on what data sources you have, you can specify those combinations. And then finally, what is the on-road operating characteristic, either the second-by-second driving traces that the vehicles are following, or a VSP bin distribution, or just average speed and facility type. Those are the three components that you need to be able to pair up together. And again, there's a variety of different resources that you can use to get this.
Great. Well, that takes us to the end of our time. Randy, I'd like to thank you for giving the great presentation, and thank all of our participants for joining us and for your great questions. Please look for a follow-up email that contains a quick survey. It'd be really great to get your thoughts on what we can do better for next time, and we're also asking for some feedback on topics you'd like to see featured in future webinars. So we'd appreciate if you take a couple minutes to fill that out. And with that, we'd like to thank you and wish you all a good rest of your day. Thank you.